All right. Good morning, everyone. Let's get started with class today. So we're gonna continue talking about algorithms today. We just have one more problem we needed to go through. You should have seen yesterday, or not yesterday, on Monday, I posted the scores to your exam on Canvas. I made a post about it last night if you haven't seen it already. In general, the exams went well. The average was around like a 40 out of 50, maybe like a 39.5 out of 50 if I'll round up. There's still
45.5 out of 50.
oh, that was like I think top 75% or something. But yeah, so it went really well, is what I would say. I wasn't sure. It's my first time teaching discrete math, so I wasn't really sure how the exam would go, but I'm happy with how it went. I'll say more about it when I pass it out on Friday. You can see statistics on it on the Canvas post that I made. And you should expect the next exam to kind of be of a similar structure and difficulty. This is usually what I aim for. It's like as long as the average is above like a, I don't know, like a 78% and at least one person gets a perfect score on it, I'm happy with how it goes for me. Yeah, so I'll say more about it later on Friday. From there, we have other things to focus on at the moment. Okay. And there isn't going to be a quiz on Friday. You took a quiz or you took an exam last Friday. It's good to have a break from these kinds of things. And I'm like a little bit behind, so I wanted time to catch up with what I need to still cover. Yeah, and then I also plan on changing quizzes a little bit, but I'll say more about that later because I haven't really thought through it.
Has a majority distribution with the majority is going between 35 and 50 points. Well, some people somehow are between 15 and 30.
Yeah, I mean, it's people are coming from different places, so it's like I don't know. It's like we're learning how to do things. Okay. Anyways, we'll talk more about this on Friday. We can chatter about the exam later on. Now we're focusing on algorithms. Okay, you're gonna have another exam in the future. Can you stop talking? Thanks. There's going to be another exam in the future. You're going to be focusing on algorithms, so we need to learn this now. Now's the best time to learn about it, and then you'll review it later on when you do the exam review. Right, so we're pretty much done with this packet, right? So algorithms, we're looking at inputs. We're putting in some input. It's going through some sort of procedure, and it's producing a desired output. And then, I mean, I've talked about this 2 times already. Let's just go to the end. So this is where we are at, right? We went through the linear search. We went through the bubble sort. We went through string matching. And then we did one where we created an algorithm where you had to add up a number of integers that you input into the program or whatever you're working with. So this is what your homework is going to look like. There's only 3 problems on the homework, but they're going to be somewhat similar to this problem, as well as the next problem as well. Which I wrote the solutions, and so we haven't gone through this yet, so ignore everything I had just written. So this is the last example I wanted to go through, and it's going to be checking to see whether or not a string that you input is going to be a palindrome. If you've done like a computer science class, you've probably seen this example before.
Palindromes are that are the same forward and backwards.
Yeah, so palindromes are strings that read the same forward and backward.
Backwards is a different word. It leaves that for a word that that is one word.
Yeah, and so what we need to do is we need to describe an algorithm for determining whether a string of n characters is a palindrome. Before I do anything, there is a function I want to mention that's going to be useful for this algorithm that we haven't discussed before. This is called the floor function. And maybe you've seen it before, maybe you haven't. This is useful when you're working with indices and you only want to go to the halfway point. You'll see what I mean later on. And so how this floor function is denoted is you have your x, and then you kind of have like these bent bars, I suppose, that kind of go a little bit beneath x. And this is going to be equal to the largest integer that is less than or equal to x. Let me make more space between 2 and x. So for example, maybe it seems a little confusing now, but all it's doing, like if you had x is equal to 2.4 and you apply the floor function to it, is this going to be equal to 2? Because this is the largest integer that's less than or equal to 2.4. And then if you did 3.9, this would be equal to 3. Right, so it's not like rounding up, rounding down. It's always going down to whatever the largest integer less than or equal to whatever your input's going to be. And so this will be useful when we're going through the following algorithm. It might be useful on the homework assignment as well. So I wanted to briefly mention what that is. And so now we'll actually go into the procedure that we're interested in. So this procedure, we're going to call it palindrome because we want to check whether or not a string that we're inputting is going to be a palindrome. And so we're going to be inputting a string. So these are really just a sequence of characters, A1 up until AN. And we're going to label the data type as a string. And so before even going through with the algorithm, it would be a good idea to go through an example to understand what this algorithm is going to look like. Pretty much all of math and probably computer science as well is really like founded on thinking through examples and then generalizing them. So it always is helpful to go through an individual example before trying to generalize something. So one example of a palindrome is the word race car.
I think I recall seeing a shirt that said Taco Cat spelled backwards as Taco Cat, so I suppose Taco Cat would be another decent example of a palindrome.
Yeah, there's plenty of examples of palindromes. There's like one that's pretty easy, or there's two things I want to focus on here. So this is an example. Like this is an example. Apparently losing my concentration. This is an example, right? Because we have like R, the first letter is the same as the last letter. If you move on to the next letter, like A, it's the same as A. Then we have C, it's the same as C. And then this is why I was bringing up the floor function, right? Is we have like this E, we have an odd number of characters that we're inputting. And so like we need to be able to terminate at the appropriate place. And so when we're going through an algorithm, it should be something like this, right? Like the first check, the first index should be comparing these two letters with one another. So this could be like I is equal to 1. And then the next thing you would want to do is you would want to compare the second letter with the second to last letter. So this would be your I is equal to 2. And then after that, we can do red or something. You would move on to the next one. So this would be like our I is equal to 3. And then all that's left is, I mean, you don't have to compare E to anything because it's in the middle. It's exactly in the middle. And so in this case, our I, we would want to terminate our program when we hit C, right? I shouldn't have drawn this. So like where we're going to want to terminate is we want to terminate. Does anyone see where we want to terminate? Or like how we would express this generally? Like we want to terminate at I is equal to 3. How can we write I is equal to 3 using the length of this string being 7? Does anyone know? It has to do with the floor function. I'll give you that much. So this was the floor function. We want to get 3 somehow from like the length of the word that we have. Yeah.
Sure. Maybe like use the division that only gives you an integer. Does that make sense?
Oh, yeah, I see where you're getting at. Like you're thinking of like modulus almost, like you're doing like a something like, well, maybe it should do like 7. Which this would be like equal to 1 or something like that. I mean, there are ways of doing that. It's not exactly what I was looking for, and that this is going to, I mean, if you divide by 2, like it's going to give you a 0 or a 1, but we want to be able to output a 3. And maybe there's like a way you can mess around with this to make it so you get the 3. What I was kind of getting at is like we want to terminate at 7 divided by 2. Like we're pretty much going to the halfway point, except like we're cutting it a little bit short. So like you do the floor function of the length of your string divided by 2, and then this would just be equal to the floor function of 3.5, which is equal to 3. So it means you'll terminate here instead of having to check like the middle character. Yeah, go ahead.
To talk of palindromes, maybe think of a phobia that I suppose could be considered an evil phobia. It's called ibophobia, the fear of palindrome. I suppose you could see the ironic evil in its in it. Like ibophobia is because it's a fear of palindrome. It's literally a palindrome in and of itself.
Yeah, it's ironic. Yeah, is that, I don't know. Does anyone actually? I feel like no one's actually afraid of palindromes, aside from maybe like 1 or 2 people in the world. Anyways, this is how the procedure is gonna go. I kind of know how this is going to. I know what the answer is going to be. So there's some things I'm going to write down, and it's kind of like, where is he getting this? Let's start like I'll talk about this answer part later on. We're initializing this answer as being true, and we'll see why I'm talking about this later on. But this is where the real like I say meat and potatoes too much, but this is where the real meat and potatoes happens. Okay, so we're gonna perform a for loop, right? That's kind of what's going on here. So we're starting at the first character, comparing it to the last, then we move on to the next character, compared to the second last, third with a third last. So this is really, we're doing a for loop here. And then again, we're starting at the first index, which is 1, and then we're terminating at this like length of the string divided by 2, and then you apply the floor function to it. So we inputted n characters, so this is going to be the floor function of n over 2. And so now we're going to perform some sort of conditional statement that's going to determine whether or not we have a palindrome. So one way of going through this is now we're comparing the characters. Like now we're in the for loop, so this means we're comparing the characters with one another. And the characters we're comparing, so if we have AI, A subscript I, we're going to say if A subscript I is not equal to A sub n, so this is the last character, and then we're going to perform some sort of subtraction. It's worth noting, like you might be thinking that there should just be A sub n minus I, but this isn't going to be exactly right. It's very close, but it's not exactly right. Does anyone see how I should adjust this to make it so it's going to be right? Yeah, go ahead.
If you wish to do the a sub n minus I, you should more accurately do a sub n minus I plus 1.
Yeah, exactly. There should be a plus 1 here. The reason why there should be a plus 1 is because the first index is 1. So if we started at I is equal to 1 and we didn't have the plus 1, we would be comparing A1 with A sub n minus 1, which would be comparing R with A, which is not what we want to be comparing with, right? We want to compare R with R. So you have to do like A sub n minus 1 plus 1, so you just end up getting A sub n. And so if these two characters aren't equal to one another, then we can set answer equal to false, which then implies that we don't have a palindrome. And then all we have to do now is just return whatever answer is going to be. Right? If it never turns false, that must mean that the answer stays true the whole time, which means that like all these characters agree with one another, which means that you have a palindrome, right? So this would mean like a sub 1 is equal to a sub n, a sub 2 is equal to a sub n minus 1, all the way up until like the whatever middle character you have, or if you have like an even number of characters, then like the floor function will just, division will just give you a whole number. So this is all that's going on with this procedure. Any questions about this problem? Yeah, and again, I remember when I first took like a computer science class, this was a really early example of like what you can do with a program. Okay, so we'll move on. That was algorithms. So, I mean, a lot of the things we'll be looking at in the future are going to be algorithms. I don't know if exactly we're going to be doing like the bubble sort, linear sort, or anything like that. But
So I put this back in my folder.
yeah, so now we're going to move on to complexity. So it's one thing to be able to write an algorithm. It's another thing to actually write an algorithm that works in a way that's as efficient as possible. And this is something people care about a lot, right? you're performing like a billion different operations, if you're able to reduce the amount of time a single operation does by even a small amount of time, it'll have huge consequences. So like we're gonna be focusing on really like how do we focus or how do we understand optimizing algorithms. So we're gonna go into complexity and the growth of functions. And so again, if you're doing like an algorithms class or focusing on optimization, what we're going to be talking about is pretty familiar or should be pretty familiar. I'm going to be introducing this big O notation. And so I think a lot of you can read the first paragraph, but a lot of what's in the first paragraph is exactly what I just read. So this section is going to introduce what's called big O notation. And then eventually we'll talk about the big omega and big theta notations as well. These are really just ways of understanding, I guess, the complexity of the function that you're working with, how many inputs and how many interactions you have. So we'll explain how big O, big omega, and big theta estimates are constructed and establish estimates for some important functions that are used in the analysis of algorithms. So I like this section because it goes pretty much right into the examples. We'll have this definition, then we'll just work on examples. So the growth of functions is often described using a special notation. This definition below describes the notation. So this is the big example or the big definition for today. This is really the primary focus, what you have to understand. So you're going to have two functions, f and g, where these functions f and g are going to be functions from the set of integers or the set of real numbers to the set of real numbers. And so we say that f of x is big O of g of x if there are constants c and k, such that we have that the absolute value of f of x is less than or equal to c times the absolute value of g of x whenever we have that x is greater than k. Right? So what this is saying is past a certain point in your domain, we have that f of x is going to be less than or equal to g of x. In a sense, it's like dominated by this function. Right. So maybe it might be easier to think in terms of this remark. When we're working through examples, we're going to be using this definition, but in terms of your intuition, maybe looking at the remark could be a good idea. So when we say that f of x is big O of g of x, this is really saying that f of x grows slower than some fixed multiple of g of x as x grows without bound. So in this picture, we have at the bottom of the page, we have two different graphs. And maybe it's color coded, but when I print it out, it's in black and white, so maybe it's hard to see. So this graph we have here, this is our c times g of x. And this function we have here, this is our f of x. And so for this example, we would say that f of x is big O of g of x, like I have here. Because we have at a certain point in time, really it looks like it's going to be this point here. Whenever we pass this x naught, it seems like we're always going to have that g of x, or c times g of x is going to be greater than f of x. So this is an illustrating example to visualize what we're talking about when we talk about this big O notation. And really, it's just going to be a bunch of examples. So this is like one of those sections where you just have to understand how to work through examples, and that's going to determine how successful you are on the exam, at least with whatever question I give you. So how to work with this big O notation, like what's like the strategy, what's the algorithm here? So a useful approach. So the main thing you want to do is you want to find constant c and a constant k. So the first thing you want to do is the first select a value of k, for which the size of the absolute value of f of x can be readily estimated whenever we have that x is greater than k. And to see whether we can use these estimates to find a value of c such that f of x is big O of g of x. Right, so maybe this isn't, I feel like this writing, I copied it from the book, it actually isn't that useful. It's just like choose c and k and see what happens pretty much, which isn't really that useful. It's really just a matter of working through examples and then developing an intuition is what I would say. So the first example we're going to look at is we're going to look at a quadratic polynomial. So we're going to show that x squared plus 2x plus 1 is going to be big O of x squared. And so the first thing you usually want to do when going through these problems is we want to find a k that is suitable. So we want to find a k such that x is greater than k. I'm going to put this in quotes because it's very vague. I'm going to say like works well. And this is going to vary from problem to problem. It really depends on the functions that you're working with. And so I would say usually, at least when you're working with polynomials, a value of k that's going to work well is going to be 1. And I'll say more about this later on. So for this example, maybe it seems unintuitive for now. I'm going to let k be equal to 1. And so this is going to allow us to have a number of nice properties. So this tells us that when x is greater than k, where k is equal to 1, this means we have, I mean, I kind of just wrote this out, but I'm going to write it again anyway. So we have x is greater than 1. And before I continue, I kind of want people to understand why I'm choosing k is equal to 1. But before I say it, does anyone see why letting k be equal to 1 so that x is greater than 1? Like, why is this going to be nice to work with? Does anyone see? Yeah, go ahead.
Values between 0 and 1, squaring them just gets smaller numbers. Will have values of 1 or greater being squared either leads to the same value or a greater value.
Yeah, that's exactly what I'm looking for, right? If we look at the polynomial we're working with, we have an x squared, and then we have an x squared in here as well. So if we allow x to be greater than 1, when we perform x squared, it's going to behave well, right? In the sense that we can say things like this, right? If we multiply both sides, so I'm going to be careful with my wording. Thus, if we multiply both sides by x, this implies that we have x squared is going to be greater than x. This isn't going to be true if x is less than 1, right? If x is less than 1, then we have x squared is strictly less than x, and then we wouldn't be able to use this equality or inequality. And then furthermore, we also have that x squared is greater than 1, right? We had x is greater than 1, x squared is greater than x, therefore x squared is greater than. And so this is kind of where, I don't know, it's maybe too dull to call it magic, but this is where the magic is. So this is like, we're going to kind of transform what we have here into something that involves x squared, right? So we have the following information now. So now we have 0 is greater than or less than or equal to x squared plus 2x plus 1. That's the original polynomial we had. And so now we want to transform all these terms so that way they involve x squared, right? So we know that x is less than x squared. So we know that this next quantity is going to be less than x squared plus 2 times x squared, right? We have x is less than x squared. Therefore, if you change this x to an x squared, we're going to have a less than or equal, or this will be like it depends on your perspective. Like this is greater than or equal to this, right? And then similarly, we said that 1 is strictly less than x squared. So if we replace 1 with x squared, there shouldn't be greater than or equal. It should be strictly greater than. It's going to be less than what we have here, right? And then where do I go from here? Does anyone see like how we finish this problem? Like why does this imply what we want to imply? Like why does this work? In showing that this polynomial is big O of x squared. Does anyone see? Okay, go ahead.
Maybe we factor out the x squared, and then it will be 4x squared, so it will be 2x all squared.
Yeah. So you can, like, really what I'm looking for, and this is what you're just saying pretty much, is we can add all of these terms together, right? This is x squared plus 2x squared plus x squared. So this is equal to 4 times x squared. And so this, now if I use the labeling that we used in the definition, this was our original f of x. And then this is our g of x, right? X squared is our g of x. Let me use a different color. And now we have, so what we have here is f of x is less than some constant multiplied by g of x, right? So this is our c. So our 4, this is our constant, this is our c. And so what we're really saying is so we're saying this like thus, we have x squared plus 2x plus 1 is strictly less than 4 of x squared whenever we have x is greater than 1. So again, this maybe it looks a little bit confusing. This is less than. So this again is our f of x. This is our g of x. And then this is our c, right? So this implies, like by definition, this must mean that x squared plus 2 of x plus 4 is big O of x squared, where c is equal to 4, and then k is equal to 1. So this is our k here. Maybe I should write that in a different color because it makes it look like I'm dividing by k. And so when you have a line like this at the end, now you can like you can use the definition and say like, so we have that x squared plus 2x plus 1 is big O of x squared. Right, so this is the general process you're going to follow when you want to show that one function is big O of another function, right? You're going to choose some k that's going to work well with the problem or the function that's given to you. It's going to depend on the context. In this example, we're working with squares, so letting x be greater than 1 worked out very well. And then you want to change whatever your original function is into something that involves whatever your g of x is going to be, which in this case was x squared. So this is going to be a common technique. So this is the most important part, I would say. It's like knowing this line and then being able to conclude that we've reached the definition. So we can conclude this function is big O of x squared. Any questions about this example or any part of like the thought process going on here? Yeah, go ahead. Oh wait, what did oh, I mean it wasn't, it's not necessary. I mean it is true, but it's not necessary. Like we are assuming x is greater than 1, so all this, but it doesn't matter. I mean, yeah, if we go into eventually we'll be talking about like big theta notation where it's like you have a lower bound and an upper bound. So I guess I put it there to be like there's lower bounds as well, but it's not relevant for this problem. Yeah. We'll talk about that later on. Yeah. Any other questions about this example, like why I did what, or anything along those lines? Yeah, so this is a good example to understand. We'll look at other examples that are a little bit different, but in terms of like a concrete example that I could ask on the exam, maybe it could look something like this. So we'll look at variations of this problem. Like we're going to look at some polynomials and then we'll generalize later on. So for this next example, we want to show that 7 times x squared is going to be big O of x cubed. And there's a couple of ways of going through this problem. We can kind of follow the same logic we did before, which is going to involve finding some value of k that's going to make it so when x is greater than k, we have like 7x squared. It's going to be less than x cubed. And then you can also kind of think in terms of like maybe defining what c is going to be and then letting k be equal to 1. But I guess like the hint here is like 7 is going to play a role, right? We have 7 multiplied by x squared. And we want to compare it to x cubed. So how I would start this one is the following. So we have this 7 times x squared. Let's make use of the 7. So I'm going to assume x is greater than 7. So in this case, 7 is our k. And then from this inequality that we have, we want to be able to compare 7x squared with x cubed. Does anyone, I would say there's like really one more observation you need to make. Like we're actually really close to being done. Does anyone see what we do with this inequality to get like 7x squared is going to be big O of x cubed? Excuse me. So we're almost there. And you should
Is
think
it
in,
something similar to, but to the last example?
sure. Yeah, I mean, we're kind of in this step right here, this process here, where we chose some x to be greater than k. And then from there, you want to be able to kind of make these kinds of statements. There's just like there's like something you want to multiply. There's like some algebra you want to perform.
So we're saying that 7x squared is less than or greater than, and 7.
Or saying like x is strictly greater than 7. Yes, Steven. Yeah, that's exactly what I'm looking for. So if you multiply both sides by x squared, then we have that this is going to give us x cubed is strictly greater than 7x squared. And this is all we wanted, right? Like this is our g of x, right? This is the function inside of big O. So this is our g of x. And then this was our f of x, right? Our f of x was 7x squared. So this is our f of x. And we're done. I mean, that's all there is to it for this problem, right? So in this case, we would have that c is equal to 1. Remember, c is what you're multiplying by g of x. We don't have anything multiplied by g of x. We just have g of x itself. So you can let c be equal to 1. And then we have k is equal to 7. And then maybe I should have like a final statement like, and we have that 7x squared is big O of x cubed. And then you could also have something like this. You can also have, so there's multiple ways of going through this. You can also have k is equal to 1 and c is equal to 7. For then you would have that 7x squared is strictly less than 7 times x cubed. Whenever we have x is greater than 1. So you could also, I mean, there's more than one answer is what I'm getting at here, right? If we choose k is equal to 1, then that means when we have that x is greater than 1, x cubed is greater than x squared. Therefore, if you multiply both sides by 7, you would have this inequality. But I think this one is more intuitive. I don't know. It probably varies from person to person. Any questions about this example? And this should be intuitive, right? Like we took something that has a second power and we're comparing it to something that has a third power. Like you should be thinking as the power increases, like if this were like O of x to the 4th power, like we should have 7x squared is going to be big O of x to the 4th, x to the 5th, x to the 6th. As the power increases, this is only getting larger, right? So as x tends to infinity, or it gets larger and larger, like this is going to be dominated by whatever
It's
the larger power is.
Like the following example simply is what 7x squared would be x cubed.
Yeah, so this next example, I mean, I was kind of building up the intuition on the previous example with what I was just saying in order to be like, you shouldn't really expect this to end up being true due to the fact that we're comparing x cubed to some squared term. Like, sure, we have a 7 in front of it, but like if x is equal to 1,000, I mean, what's 7 at the end of the day? Like 1,000 times 1,000 times 1,000, it's much larger than like 7 times 1,000 times 1,000.
Or just have if it's much simpler, you can do x at x equivalent to 10 and you'd still find that at x squared is 100 times 7 is 700. Well, 10 cubed is 1,000.
Yeah, so by like in the beginning, like you kind of want to determine what your gut says about this being true or untrue, and it should be like screaming that it's untrue, right? And so we're going to go through a proof by contradiction. So we're going to suppose we have x cubed is less than c, some constant multiplied by 7x squared for all x greater than some value of k. Right, so what I'm assuming now is I'm assuming that x cubed is big O of 7x squared. This is really what this is saying here. And maybe, and pencil users are gonna hate me, but maybe you should do like by contradiction. should specify in the beginning what method you're using. That way you're not confusing the reader. So by contradiction, we're going to suppose that x cubed is big O.
To solve that issue, I had to put an up arrow right in between the bullet point and suppose with the by contradiction above the up arrow.
Yeah, that's good. Yeah, and so we're going to be supposing that this inequality holds true for all x greater than k. And so kind of what the idea here is, like, you have an extra power of x on the left-hand side than you do on the right-hand side. And that's going to be problematic in that now, if we were to divide both sides by x squared, we'll get the following. So maybe I'll say like, so if you divide both sides by x squared, this will tell you that x is going to be less than c times 7 for all x greater than k. Does anyone see what the problem with this is going to be? Like, why is this going to be a contradiction?
X is greater than k. I wonder if it maybe has something to do with the fact that the comparison operators are not the same.
Not necessarily. There's kind of like two words I'm looking for here. Like the first word is, this is a constant, right? We're doing a constant multiplied by 7. So this is just a fixed value, right? So maybe c is equal to 10, maybe it's 100, but it's just going to be like these, it's a constant. So we're doing like a constant. So this is equal to some fixed number, right? Maybe it's like 1,000, maybe it's 1,000,000, but x is a variable, right? We're assuming x is greater than k. And so x can be like any large number. Like x can be 1,000, it can be 1,000,000, a trillion, like it goes to infinity. So like there's never going to be a constant that's always going to be greater than x, right? So this is a variable. It can be any real number, right? So like the main thing I'm getting at, maybe I should put it into words because I'm not sure if people are getting this. So what this is saying is that 7 times c is a constant. While we have that x goes to infinity as a variable. And so what you're saying is like you can make some constant that's going to be greater than every single real number, which is impossible, right? Like this could be like 1,000,000 and this could be like 7,000,000. You can just make it so x is 7,000,001 or something like that. Or it could be 1,000,000,000 or what have you. So this is impossible. Or maybe I should say which is impossible. I.e., we've reached a contradiction. And so the conclusion we can make now is x cubed is not O of 7x squared. That's the conclusion. And again, it should be intuitive. This is a larger power. This is a smaller power. So you shouldn't really expect it to, you really shouldn't expect it to be like big O of 7x squared. Any questions about this example? Okay. Yeah, so we'll move on. This next example kind of generalizes what we've been doing so far. So here we're looking
at the theorem.
Yeah. So this theorem, we're looking at a general polynomial where a naught, a1, a sub n minus 1, all up until an are real numbers. And we want to show that f of x is going to be big O of x to the n. That is to say, if you have a polynomial of degree n, that polynomial is going to be big O of x of n, right? So the n's here are matching. That's the main observation. And so before I go through this, there's one thing I want to point out. Maybe you've seen this, maybe you haven't. If you have the absolute value of a sum of two numbers, this is going to be less than or equal to the sum of the absolute values. So you've probably seen this before in like an earlier math class or something like that, but it's not equal. It's going to be less than or equal to. So this is going to be important for the next example that we work. Right, so for this theorem, just like we did before, like usually when you're working with polynomials, I'm just going to say this outright. Like if you're working with polynomials, usually you're going to want to let x be greater than 1. like this is going to be your k. Right, so usually you're going to want to let your x be greater than 1, so that way everything works out in a way that's useful. And let's just start with looking at the absolute value of f of x, right? So we're going to start with the absolute value of f of x, and by the end of this problem, we want to be able to say that this is going to be less than or equal to c times x to the n. Right, that's the entire point of this, is to show that it's going to be big O of x to the n power. And so we just use what's given to us, right? So we have f of x is equal to this general polynomial.
Writing down that less than or equal to c times x to the n. Just, yeah.
Yeah, I mean, maybe it'll end up being exactly here. Maybe I'll move it eventually. But this is like what we want to end up showing. Right, so this is equal to the absolute value of a sub n times x to the n power plus sub n minus 1 times x to the n minus 1, all the way to this plus a naught. So I'm just substituting in what we had for f of x here. And now we want to make use of what I just had written above, right? So we can distribute the absolute values, but we have to make sure that we include the less than or equal to sign. So this is really going to be less than or equal to the absolute value of a sub n times x to the n. We have x is greater than 1, so every single term involving x is already greater than 0, so you don't have to write the absolute value around it. This will be plus the absolute value of a sub n minus 1 times x to the n minus 1, all the way up to the absolute value of a naught. And so the big idea here, to kind of outline this strategy or what we want to be doing, is we want to get x to the n at the very end of this multiplied by some constant c. And if you look at what we have now, we do have an x to the n and various powers of x, and they're all being multiplied by some constant. What?
That fraction close to value, is that 8 sub 8? Is that a of 0?
Oh yeah, this is a sub 0, like what we had above. Yeah. So I have this constant here. And so we want to somehow go from here to here. And really the idea is we're going to factor out x to the n, which maybe seems like, how do we do that? We only have one x to the n. We're allowed to use division because we have x is greater than 1, right? Because we have x is greater than 1, we're allowed to have like x in the denominator and powers of x in the denominator. So what you want to do now is you want to factor out x to the n. And if you factor out x to the n, this is x to the n, and then you have the absolute value of a sub n plus the absolute value of a sub n minus 1. If we factor out x to the n, this means that we're really going to have the absolute value of a sub n minus 1 divided by x. Because now if you multiply x to the n by what we have here, it's going to produce this x to the n minus 1. And so you can continue this process until you eventually have this a sub 0 divided by x to the n. And we're getting closer. There's still a little bit of work. I need a little more space, so I'm going to erase this k here. We're getting a little bit closer, but we're not completely there yet, in that we almost have a sum of constants, except we have like these pesky x's in the denominator. But we're allowed to include less than or equal to signs, right? And we also know that x is greater than 1. And so what this means when you combine all that information together is that this is going to be less than or equal to x to the n times the absolute value of a sub n plus the absolute value of a sub n minus 1, all the way up until the absolute value of a sub n, or a sub 0, right? All I did was I removed the division by x. This is going to be less than just the constant itself due to the fact that x is greater than 1. So we're dividing by something greater than 1, which is making the constant a little bit smaller. And now we're pretty much done, right? In the sense that we have x to the n multiplied by a constant, right? So this is going to be our c. And so if you write this as your c, this is really just the same thing as saying that this quantity we have here is equal to C times x to the n power, right? So what we've shown is that this absolute value of f of x is less than or equal to C times x to the n. And then we can say, like, thus, we have that f of x is big O of x to the n. Right, so this is how these proofs usually go. Like, there's some sort of like fancy mathematical manipulations you perform in order to eventually get into, let's see. What's up?
What's that diagonal line at the end for?
Oh, it was like a check mark. It doesn't mean anything. I want to go through one more problem. The next one's quick, so I have enough time. Any questions about this one though before I move on? Okay, I want to make sure I don't actually like fall behind perpetually, so I want to make sure I go through this next example quickly. So this next example, it's asking how big O notation can be used to estimate the sum of the first n positive integers. And so the sum of the first n integers is 1 plus 2 all the way up until plus n. And I don't have that much time, so I'm going to kind of spell out what this is going to look like. So the main idea here is we have like 1, 2, all the way up until n. Like everything before n is going to be less than n. So if you replace all of these numbers with an n, the following inequality would hold. This is the same thing as n plus n with itself. And you're performing this addition n times. And so if you're adding n to itself n times, this is really the same thing as doing n times n. So this is equal to n times n, which is equal to n squared. Right, and so what we're saying is that if you take the sum of the first n numbers, it's always less than or equal to n squared. And so what this is really saying in this big O notation is the following. So what we're saying is that this sum of the first n integers is big O of x squared. And what we have here is, I guess we have C is equal to K is equal to 1. Right? Because we had, like, this is 1 times n squared, and then the sum is less than or equal to that. Right? So you can even write out sums, or like you can use big O notations for sums. Sums are just functions at the end of the day. Yeah, question?
Is it O of x squared, or do we have to write O of x?
Oh, I think you can, it's probably better. I mean, either way, really. But I mean, I used n, so I should use n squared. That's what I would say. Yeah, I mean, it's kind of like a change in variable, and like we're thinking of something finite now instead of something in. But yeah, I think that was a good point to make. Any questions about this example? Okay, so we'll continue with this in Friday's class. But I think you kind of know the important parts of this problem. Yeah, so remember, there's a homework on Friday. It's just 3 problems, and then there's not going to be a quiz on Friday. I'll pass back the exams, and we'll talk about it a little bit.